Welcome! Today, we'll be diving into LeetCode problem number 293, titled Flip Game. This problem challenges us to think critically about string manipulation and efficient iteration. Let's explore the problem and its potential solutions together. In this problem, you are playing a flip game with a string made up only of the characters plus and dash. The objective of the game is to find all the possible states of the string after performing one valid move. A move is defined as flipping two consecutive plus characters into. If no such move is possible, the result should be an empty list. The input to the problem is a string s of length n, where n is between 1 and 500. The output should be a list of strings representing all valid states of s after one move. For example, consider the string plus 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 plus. If the input string is plus 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 plus, the output would be a list containing three strings, plus plus, plus plus, plus plus. Here's why: the string has four consecutive plus characters, allowing three valid moves. In the first move, flipping the first two plus gives plus plus. In the second move, flipping the middle two plus results in plus plus. Finally, flipping the last two plus gives plus plus. Since these are the only possible states, the output includes all three. Now, let's look at another example with the input string plus plus. For the string plus plus, the output is plus dash. This is because there are only two consecutive plus characters at the beginning of the string. Flipping these two plus characters results in the string plus dash. No other pairs of consecutive plus exist, so the output contains just this one state. Meanwhile, if you consider a string like dash plus, the situation is different. In the case of the input string dash plus, the output is an empty list. This is because the string does not contain any pair of consecutive plus characters. Since no valid moves can be made, the result is simply an empty list. Now, to ensure your solution handles all scenarios correctly, there are a few constraints and edge cases to consider. First, the input string can be as long as 500 characters, so your solution must be efficient in both time and space complexity. Additionally, you should handle edge cases like single character strings, strings with all dash characters, or short strings like plus dash where no valid moves exist. In all these cases, the output should be an empty list. By addressing these conditions, you can ensure your solution works for all possible inputs. To start solving this problem, let's explore the brute force approach. The intuition here is straightforward: we iterate through the string, checking each pair of consecutive characters to find any occurrence of the sequence plus plus. If we find such a pair, we flip it to and record the resulting string as a valid new state. Breaking it down step by step, we first traverse the string using a loop. At each index, we check if the current character and the next one are both plus. If they are, we create a new string where this pair is flipped to. This modified string is then added to our result list. However, because each flip operation generates a new string, the time complexity becomes O, n squared. This is due to the O, n, traversal being combined with the O, n, cost of creating new strings. Additionally, the space complexity is O, n asterisk m, where m represents the number of valid states generated. This is because we need to store all these new strings in memory. While this approach is simple and effective, it's important to note that it can become costly as the input size grows. Now, let's consider an optimized approach to address the memory overhead of the brute force method. The logic remains the same: traverse the string, find valid plus plus pairs, and flip them, but instead of storing all the resulting states in a list, we optimize by using a generator. A generator allows us to yield each valid state dynamically, which means we don't need to allocate memory for all states at once. The steps are similar: we loop through the string, identify valid positions for flips, and dynamically yield each new state as soon as it's created. While this reduces space complexity from O, n asterisk m, to O, 1, since we're no longer storing the full list in memory, the time complexity remains O, n squared. This is because the traversal and string creation processes are still the same. Ultimately, we chose the brute force approach over the generator method. This is because the problem explicitly requires generating all possible states, and storing these states together is often more practical when further processing is needed. The brute force approach is straightforward and meets the problem's requirements effectively. There are a few key observations that further clarify the constraints and trade-offs in this problem. First, only ++ pairs are eligible for flipping, which simplifies the task as we don't need to consider other combinations. Second, the output-specific nature of the problem means we must generate all valid states. There's no way to optimize by stopping early or skipping potential flips. Third, Python's string immutability plays a significant role here. Since modifying a string creates a new one, this contributes directly to the O(n)² time complexity. When comparing the brute force and generator approaches, the main trade-off lies in memory usage versus practicality. While the generator reduces space usage, it's less suited to scenarios where the full list of states is needed for further processing. The brute force method, on the other hand, is more intuitive and aligns well with situations that require storing or analyzing all results together. Lastly, in terms of scalability, the O(n)² complexity is acceptable for small to moderate input sizes, but for very large strings, additional constraints would be necessary to keep the problem computationally feasible. Overall, the brute force approach strikes a good balance between clarity, performance, and simplicity, making it a suitable choice for this problem. In this problem, we're given a string made up of only plus and dash characters, and our goal is to identify all possible strings that can be created by flipping exactly one pair of consecutive ++ into. We are tasked with returning these transformed strings as a list. To achieve this, we'll break the algorithm into clear, actionable steps. First, we need to parse and understand the input. The string S contains only plus and dash characters, and the key is to find every instance where two consecutive plus characters appear. When we find such a substring, we replace it with, creating a new string. We then store each transformed string in a dynamic result list. This list will hold all valid outputs, and will return it at the end. Now that we understand the input and the output requirements, let's move on to the detailed steps of the algorithm. The next step is to traverse the string to identify pairs of ++. We use a loop with an index I to iterate through the string. To avoid going out of bounds, we stop the loop at len s1, since we're checking pairs of characters. At each step, we check if the substring s, I+2, equals ++. If we find such a pair, we create a new string by flipping this ++ into. To do this, we use slicing to keep the parts of the string before and after the flipped segment, and then concatenate them with the flipped. This new string is then added to the result list. Once this is done, we continue looping to check for additional ++ pairs in the string. After the loop completes, the result list contains all the valid strings, and we return it as our final output. There are a few key insights that make this algorithm both efficient and robust. First, the traversal of the string is straightforward and linear, as we only need to check consecutive pairs of characters. This ensures the time complexity remains O(n), where n is the length of the string. Second, because strings in Python are immutable, we can't modify a string directly. Instead, we use slicing and concatenation to construct new strings. While this approach introduces some overhead, it's manageable given typical input sizes. Third, it's important to handle edge cases. For example, if the string is empty, no transformations are possible, so the result would be an empty list. Similarly, if there are no ++ pairs in the string, the output is also an empty list. On the other hand, if the string consists entirely of ++, each consecutive pair creates a unique transformation. The algorithm is also capable of handling strings with mixed plus and dash characters seamlessly. To implement this algorithm effectively, we rely on two main data structures. The first is the result list, which dynamically collects all the transformed strings. This list is essential because we need to store multiple outputs as we find and flip each ++ pair. The second is string slicing, which allows us to create new strings after flipping ++2. By using slicing, we can efficiently separate the parts of the string before and after the flipped segment, and then concatenate them with the modified portion. This approach ensures that the original string remains unchanged while enabling us to generate all possible transformations. Let's walk through an example to see the algorithm in action. Suppose the input string is s equals ++++. We start with an empty result list, result equals. As we loop through the string, we first check the substring at I equals 0, which is s, 0:2, equals ++. Flipping it results in the string plus plus, which we add to the result list, making it result equals plus plus. Next, we move to I equals 1, where the substring s1:3 equals plus plus is flipped to, resulting in the string plus plus. We add this to the result list, updating it to result equals plus 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 plus. At I equals 2, the substring s2:4 equals plus plus is flipped to, giving us the string plus plus. Adding this to the result list gives the final output, result equals plus 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 plus. We then return this list as the result. Finally, let's analyze the algorithm's complexity. The time complexity is O(n), as the string is traversed once in a single loop. Each time we find a plus plus pair, we perform slicing and concatenation, which technically takes O(n) time. However, since this happens a limited number of times proportional to the number of plus plus pairs, the overall complexity remains linear. The space complexity is O(k*n), where k is the number of plus plus pairs, and n is the length of the string. This accounts for the storage of each transformed string, as each new string requires O(n) space. Overall, the algorithm is efficient and well-suited for small to moderate input sizes. This Python implementation solves LeetCode problem number 293, flip game, efficiently. The task is to generate all possible strings from a given input string s by flipping exactly one pair of consecutive plus plus substrings to. The code begins by defining a class solution, and within it, the method generate possible next moves. This method takes the string s as input. First, an empty list result is initialized to store all valid transformations of the input string. This list will eventually hold all the strings resulting from flipping each plus plus substring to. The next step involves iterating through the string s using a for loop. The loop runs from index 0 to len s2, the second to last character, to ensure that each character and its immediate next character are checked as a pair. Within the loop, there's a condition that checks if the current character s, I, and the next character s, I plus 1, are both plus. If this condition is true, it means we have found a plus plus substring. The code then creates a new string by concatenating three parts: the portion of s before I, the flipped, and the portion of s after I plus 2. This new string is added to the result list. Once the loop has checked all pairs in the string, the result list, containing all valid transformations, is returned. This implementation is efficient, with a time complexity of O(n), where n is the length of the input string. The algorithm ensures that every possible flip is considered, and by appending to the result list, it neatly encapsulates all possible outputs. The code handles edge cases like an empty string or strings without consecutive plus characters by simply returning an empty list, as no transformations are possible in those cases. This is the Java implementation of the flip game problem, directly mirroring the Python logic. The method generate possible next moves takes a string as input, identifies all possible transformations where consecutive plus plus can be flipped to, and returns them as a list of strings. Key differences from Python include type declarations, the use of list from Java's collections framework, and string manipulation methods like substring and charat. The logic remains identical to the Python version. In this problem, we are tasked with finding all possible states of a string after flipping each occurrence of consecutive plus plus into. The input string, s, consists of plus and dash characters, and the output is a list of strings showing all valid transformations. Let's consider an example where the input string is s equals plus 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 plus. To solve this, we start by initializing an empty result list, result equals, which will store all our valid transformations. Next, we set up a loop to iterate through the string, with the range going from I equals 0 to len s2. This is because we're checking pairs of characters, and we need to ensure we don't go out of bounds. Now, during the first iteration where I equals 0, we check if s, I, and s, I plus 1, are both plus. In this case, s0 and s1 are indeed plus, so the condition is true. As a result, we replace this plus plus with, creating a new string. The new string becomes plus plus by updating the first two characters, while keeping the rest of the string intact. We then add this transformation to our result list, so now result equals plus plus. Now, let's look at the second iteration, where I equals 1. Again, we check if s1 and s2 are both plus. This condition evaluates to true, so we replace the plus plus at index 1 and 2 with. The new string is constructed as s, I, plus plus s, I plus 2, which simplifies to plus plus in this case. We then add this new transformation to the result list, so it becomes result equals plus 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 plus. Next, during the third iteration, or I equals 2, we perform the same check for the characters at s2 and s3. These are also both plus, so the condition is true once more. We replace this plus plus with, resulting in the string plus plus. This transformation is added to the result list, giving us result equals plus 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 plus. At this point, we have reached the end of the loop since there are no more pairs of characters to check. The final output for this example is the list plus 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 plus, which represents all valid transformations of the input string. Let's now consider another example where the input string is s equals plus dash plus plus. We start with the same initialization process, an empty result list, result equals, and a loop range from I equals 0 to len, s2. In the first iteration, where I equals 0, we check whether s0 and s1 are both plus. In this case, s0 is plus, but s1 is dash. Since the condition is false, we skip this iteration and move to the next. During the second iteration, where I equals 1, we check the pair s1 and s2. Again, s1 is dash, so the condition is false, and we skip this iteration as well. At this point, we have not yet found any valid transformations, so the result list remains empty. In the third iteration, where I equals 2, we check the pair of characters s2 and s3. This time, both s2 and s3 are plus, so the condition is true. We proceed to replace the plus plus at index 2 and 3 with. The new string is constructed as s, I, plus plus s, I plus 2, which simplifies to plus in this case. We add this transformation to the result list, so now result equals plus. With this, we reach the end of the loop. The final output for this example is the list, plus, which contains all valid transformations of the input string. The time complexity of our solution is O, n, where n is the length of the input string s. Let's start by breaking this down. First, we have the main for loop, which iterates from index 0 to len, s2. This means the loop executes n 1 times, which is clearly O, n. Next, we perform substring operations whenever a valid plus plus is found. Specifically, we create a new string by slicing s, I, and s, I plus 2 and concatenating them with in between. Now, slicing s, I takes O, I, while slicing s, I plus 2 takes O, and 2. Combining these substrings involves concatenation, which is O, k, where k is the total length of the resulting string. Since these operations are dominated by the length of the string s, we can simplify this to O, n. In the worst case, if every pair of plus plus is replaced, this operation is repeated O, n, times throughout the loop. This gives us a worst-case time complexity of O, n, asterisk O, n, equals O, n squared. Now, considering the overall complexity, we see that substring creation and concatenation occur at most once per iteration of the loop. Since the loop itself has O, n, iterations, and each substring operation is O, n, the worst-case time complexity becomes O, n squared. However, in practice, we only append to the result list when a valid plus plus pattern is found, so the actual number of substring operations is typically less than the number of iterations, making the practical runtime more efficient in many cases. Moving on to space complexity, the solution requires O, n, space in general. This is due to the temporary strings generated during substring operations. For instance, every time we create a new string using s, I, plus plus s, I plus 2, we allocate memory proportional to the length of the string s. In the worst case, if there are O, n, transformations, this means O, n, temporary strings. However, these strings are stored directly in the result list, so no extra memory is consumed beyond their own creation. Additionally, the result list itself contributes to space usage. In the worst-case scenario, if every pair of consecutive plus plus leads to a transformation, the list could hold up to O, n, strings, each of length O, n. This results in a total memory consumption of O, n squared, for the result list alone. As for auxiliary space, aside from the input string s, the result list, and the temporary strings, the solution does not use any other significant data structures. This means the auxiliary space remains constant at O(1). Overall, the dominant factor in space complexity comes from the memory required for the result list, giving us an overall space complexity of O(n)² in the worst case. When comparing this solution to a brute force approach, which might generate all possible substrings of S, the improvement becomes clear. A brute force approach would have a time complexity of O(n³), as it involves generating and validating all substrings. By focusing only on consecutive ++ patterns and directly generating valid transformations, our approach avoids this inefficiency. Looking at the best, average, and worst-case scenarios, we get a clearer picture of the solution's efficiency. In the best case, if the string S contains no ++ patterns, the loop completes without making any transformations. This results in a time complexity of O(n) and a space complexity of O(1), as no new strings or transformations are created. In the average case, where the string has a mix of valid and invalid patterns, the time complexity is still O(n), as the loop runs linearly. However, the space complexity depends on the number of transformations and typically remains O(n) for a moderate input. Finally, in the worst case, where the string consists entirely of consecutive ++, the time complexity becomes O(n)² due to repeated substring operations, and the space complexity also reaches O(n)², driven by the result list storing all possible transformations. Overall, this solution strikes a balance between clarity and efficiency, handling typical inputs well while avoiding the pitfalls of brute force methods. When solving the flip game problem, there are several common mistakes to watch out for. One of the most frequent errors is not considering all possible flips. For example, after finding the first valid transformation, it can be tempting to stop there, but this approach risks missing other potential paths that could lead to the optimal solution. Another issue arises when trying to modify the input string directly. Since strings are immutable in many languages like Python and Java, attempting to change them directly will either throw an error or fail silently. To work around this, you should convert the string into a mutable data structure, such as a list of characters, before making modifications. Additionally, it's crucial to handle edge cases effectively. These might include situations where the string is very short, contains no ++ pairs, or is already fully transformed. Testing these scenarios thoroughly ensures your solution is robust. Inefficient backtracking is another pitfall. Revisiting the same state repeatedly can lead to redundant computations. To address this, use memoization to store and reuse results from previously visited states. Lastly, always pay attention to the problem constraints. For instance, if the task requires limiting recursion depth or optimizing time complexity, a straightforward brute force approach may result in time limit errors. Strategies like these are essential for crafting an efficient solution. Now, let's focus on insights relevant to interviews. One key skill is recognizing patterns in problems. For flip game, the need to systematically explore all valid transformations points to backtracking or depth-first search as ideal approaches. Interviewers often assess your ability to optimize these solutions, so incorporating techniques like memoization to reduce redundant computations can give you an edge. Discussing edge cases before diving into the code is another valuable step. It demonstrates analytical thinking and thoroughness, qualities that interviewers highly value. Additionally, problems like this often involve subtle bugs during string manipulation. Being able to debug effectively and reason through your code step by step is a critical skill. Furthermore, connecting the problem to real-world scenarios can set you apart. For example, you might relate string manipulation here to tasks like parsing, input validation, or tracking game states in software applications. This not only showcases your technical understanding but also your ability to see the bigger picture. To deepen your understanding, it's helpful to explore related problems. For instance, LeetCode 294, Flip Game 2, builds on this problem by asking whether the starting player can guarantee a win. Another example is LeetCode 22, Generate Parentheses, which also involves recursive exploration of valid states. Similarly, LeetCode 46, Permutations, requires generating all possible states through recursion, and LeetCode 51, Nqueens, involves backtracking and systematic state exploration. Beyond related problems, it's useful to consider alternative approaches and their trade-offs. The brute force approach is a good starting point because it's simple to implement. However, it becomes inefficient with larger inputs due to the exponential number of transformations. While this approach is educational, it's not scalable. On the other hand, backtracking combined with memoization significantly improves efficiency by preventing the re-evaluation of already visited states. Although this method is more complex to implement, it provides a much better balance between clarity and performance. Another approach to solving the problem is iterative simulation. Instead of using recursion, you can manage state exploration with a stack in an iterative manner. This has the advantage of avoiding recursion depth limits, which can be a concern in languages that impose strict limits on recursion. However, this method can sometimes be less intuitive compared to backtracking, especially when visualizing the transitions between states. The trade-off here is between avoiding potential stack overflow issues and the added complexity of debugging an iterative solution. Depending on the constraints and requirements of the problem, this approach might be worth considering, particularly when recursion limits pose a challenge. Great job! We've covered the flip game problem and discussed a brute force approach to solve it. Remember, tackling problems step by step builds foundational skills. Keep practicing, and I'll see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!